So welcome back again. So if you recall, in my last class, we were dealing with Green's theorem. Okay. So what was Green's theorem? Say, suppose, C is a positively oriented, then what else? Then piecewise smooth and simple closed curve, and if it bounds a region D, then the line integral of this is given by this. So basically, it gives us a relationship between a line integral and a double integral. Okay, fine. So if you recall, we proved this Green's theorem for simple reasons. Okay, and what are simple reasons? The reasons in 2D plan which can be expressed both as a type 1 and type 2 region. Okay, so today what we are going to do, we are going to discuss about this extension of Green's theorem to general reasons. General reasons. Okay. So basically, we will be dealing with extension of Green's theorem to general reasons. That's what we are going to do. Okay. So that means the reason doesn't necessarily have to be a simple reason, but somehow, if we are able to convert it into the union of some simple reasons, we are fine with that. Okay. So I'll just show you the tricks how we are going to accomplish that. Okay. So suppose I have a reason like this. So obviously, this reason, the way I have drawn, is it both a type 1 and type 2 reason? Just a minute. Is there anywhere? Yeah, I think I have certain reasons over here which will prevent us from explaining it as a type 1, both as a type 1 and type 2 reason. Okay, and let us assume that this is the region we are considering, and suppose your I'll change it later on. Suppose this region is bounded by this curve C. As you can see that it is positively oriented, because you will see the region always on its left if you are moving in this direction. Okay. So now what we are going to do? We are going to divide this region in such a way that it becomes the union of two your simple reasons. Okay, and for that what we have introduced a vertical line here, say. And remember, it doesn't necessarily have to be vertical line. Okay, so it can be any curve. Okay, through which you are dividing a certain reason into union of simple reasons. Okay, so now let us assume that this part is given by, say, C1. This part is given by C1. Okay, so that means if I take this part in the opposite direction, that is going to give me minus C1. Okay, fine. Now, suppose my original reason was D, and now this D, through the introduction of this vertical line, in fact, such lines or curves, they are called crosscuts. Okay, they are called crosscuts. Okay, so then what is going to happen? Your D is going to be union of D1 union D2. Okay. So now, if we use the property of your multiple integral, so then obviously dp this is simply going to be, I mean, d1, okay, whatever it is here, plus d2, isn't it? Over here, in case of dot dot, you have this integral. Is it okay? Fine. Okay. So
Yeah.
now you can see that I mean d1 being a simple region here, d1 being a simple region here, and suppose I call this part as say let's see. Let me call this one as C3 now. I'm going to call it as C1, that green part, the green part of the curve. I'm going to call it as C1. And suppose this part, let me call it C2. So basically, C is the union of C1 union C2. Okay, fine. So then what is going to happen? Now from
But
here.
you have written U2.
Oh, sorry. C2. Sorry. Thank you. So now let us concentrate on D1. So then you can see that maybe okay. Just a minute. Maybe what I'm going to do is anti-clockwise direction here. Let me call it as C3. Not necessarily, I mean, anti-clock, but for this reason, this is anti-clockwise oriented. And let this be C3, and the direction opposite to that be minus C3. Okay, so that I mean, for the first reason, it is easier for me to explain things. Okay, so then you will see that your D1 is bounded by the union of C1 and C3. Is it okay?
Yeah.
Right? And then this region D2, it is bounded by the curve C2 and minus C3. Is it okay?
Yes.
Fine. So that is why this one, if I again convert it back to, I mean, a line integral through the use of Green's theorem. So this is going to give me your, I mean, C1 union your C3, and then again, I mean, your P dx plus Q dy. And for this one, I'm going to get C2 union minus C3 P dx plus Q dy. And they will be closed curve. I'm using this symbol. Okay. So then what is going to happen from here? And again, if I use properties of line integral, so this is going to give me what? Your C1. This is going to give me this integral over C1 plus this is going to give me C3, and then again C2, and then again this is going to be minus C3, isn't it? Plus integration over minus C3. But this I can write as minus of this. Is it okay? Fine. So then what is going to happen? This one and this one is going to negate each other. Okay? Fine. So basically, eventually what it becomes? Eventually it is going to become the union of C1 union C2. Okay? And C1 union C2 is simply C. Is it okay?
Yeah.
Fine. So that means whether the reason is simple or not, reason is simple or not. If we have a reason bounded by a positively oriented, piecewise smooth, and simple closed curve, then your Green's theorem you can always apply. Okay. So this is the first thing. So now how we are going to make use of it. So let us just simply work out one example, and after that, I will show some more application, or you may consider that to be, extension of Green's theorem to general reasons. Okay, so let us try to work out this one. Dx plus 3xy dy. You have to evaluate that. And where C is the boundary of the semicircular region D in the upper half plane between the circles, x squared plus y squared equal to 1 and x squared plus y squared equal to 4. So basically what is being given, like say so the green curve, this green curve is my C. This green curve is my C. Okay? And this is my region D. Okay? So you have to perform integration of this over, you have to perform line integral for this curve. And what I would like to do, I'd like to use Green's theorem to reduce it into a much simpler form. Okay? So now, obviously, you can see that this particular region, originally, region D is not simple. But if you use this vertical crosscut, then you can easily convert it into two simple regions, right? Since we already know the theorem, that is going to work for any region. So that is why for this, if I use Green's theorem, so this is going to give me your del x. What is q here is 3xy. So 3xy minus del y. P is nothing but this. Okay. dA. Fine. And then this is going to be equal to D. You know that this is going to give me 3y, this is going to give me 2y. So basically, I am simply going to get y dA, right? And you know that this region, if I express it in polar coordinates, my job is going to be much easier. Okay, so what I will do, I will simply use r cos theta and r sin theta for x and y. So, and that is going to give me r goes from 0 to 2, then theta goes from 0 to what? Pi. Because I am considering only upper half of the plane. Okay, fine. 0 to pi, and you can see that here the variables r and theta are separable because what is happening here? Here the limits, they are fixed. Okay, so I may write it as r1 to 2 is r squared here, and then theta going from 0 to pi, then sin theta d theta, and you can easily integrate it, right? Okay, so that is one. So now let us see whether we can apply Green's theorem in regions with holes. Green's theorem in regions with holes. Okay, fine. So basically we are going to do with holes. Okay, so basically we are going to consider your multiply connected regions. For that, what I'm going to do, say suppose I am considering a region bounded by these two curves. I still haven't shown any orientation of the curves. I mean, this is only doing it. Okay. Obviously, you understand that. I mean, the shaded portion is the region under consideration. Okay. And suppose this outer curve it is C1 and this inner curve is C2. Right. So what I would like to do, I would like C1, both C1 and C2 to be positively oriented so that I can use Green's theorem here. Okay, fine. So now, what is happening out here? What is happening out here? So if C1 has to be a positively oriented curve, so then the region under consideration must be towards your left as you move along the curve, isn't it? So in that case, I will have this anti-clockwise direction. But for C2, if you want the region under consideration to be left, then your orientation should be this, that is clockwise direction. Is it okay?
Yeah.
Fine. So that is why we are taking it as this. So now, as before, what I am going to do, I am going to divide the whole region D into two regions D1 and D2 by the introduction of these crosscuts. So then what I'm going to do here, I'm going to have two directions, this one and this one, and similarly, just a minute. Here, I mean, again, it is up to you in which direction you take. So here, let me take in this direction and let me take in this direction. Okay, I'm not going to even name them. So what I would like to tell you is that, see, now what is happening out here? Like, if I consider the double integral, if I consider this double integral, say your del q del x minus del p del y dA. So then it is simply going to be your this d1 dA plus d2 dA. And please remember this dot I haven't written anything. So here dot it will be replaced by del q del x minus del p del y. Is it okay? Fine. So then again you know that here now I mean if I apply Green's theorem, in the regions D1 and D2 separately, then what is going to happen? Eventually, see here, you will see how I am going to take. Now, in this region D1, say I was moving along this curve. Then I am moving along this, and then again this. So I'm completely getting a positively oriented curve. Is it okay? Fine. Now, if I want to consider the region D2, so then what I'm going to do, I'm going to move along this. Again, it is anti-clockwise. This, fine. Then this, and then this. See, the orientation of C2 is preserved, isn't it? So then what is going to happen? Eventually, after breaking all these line integrals, you know that line integrals along these two, along this crosscut, right? They are going to negate each other. Similarly, along this crosscut. Okay. So eventually, what I am going to have, I am going to end up with again. What I'm going to have, I'm going to have simply C1, I mean P dx plus Q dy, and then again C2 P dx plus Q dy. Is it okay? Are you getting my point?
Yes.
Fine. And if C is the union of C1 union C2, so then again you can see that your Green's theorem you can apply. Green's theorem you can apply for what? Simple, multiply connected region as well. But the thing is that you have to be careful about your orientation of the inner closed curve. Is it okay? Fine. So now let us try to do an application of this fact, application of whatever we have done just now. Okay. So okay, so this exercise is your, say, if your y squared j show that your FDR, so this is equal to 2 pi, this is equal to 2 pi for every your positively oriented curve, positive oriented simple closed path, oriented simple closed path that encloses the origin. Okay, so this is a very interesting example. So here, what we are going to do, say, suppose, I mean, this is my xy plane, and of course, this is the origin. So what is given here? Say, suppose, I mean, suppose I take any positively oriented closed curve C. So then, if you look at this, if I use f to be equal to p dx, pi plus qj, so then you know that your f dot dr, this is simply p dx plus q dy, isn't it? Right? Is it okay? Fine. So that means we have been told simply to evaluate p dx plus q dy along the curve C. Is it okay?
Yes.
Yeah. Fine. So now, say here, one thing you have to remember is that we haven't been given any region, because if I want to, evaluate this line integral, independent of Green's theorem, right? Then we are not even worried about, what region it encloses, isn't it? Is it okay? Fine.
Yeah.
But now, what we are going to do, we are going to introduce a very small circle. We are going to introduce a very small circle here. Very small circle here. Okay. And remember, this small circle, what I'm going to do, I'm going to keep it so small. Say of radius epsilon. So that, this circle is enclosed by the original curve C. Okay, so let me call this circle, and again I am going to take anti-clockwise orientation for this circle. I am going to call it C1. Okay, and it is of radius say epsilon. Okay, so now what I am going to do? Then you know that if I consider the closed curve minus C1, so then what is going to happen? Along this direction, I am going to have minus C1. So that means if I consider the region enclosed by the curve C and minus C1, right? So both are going to be positively oriented with respect to the region D that they enclosed. Is it okay?
Yeah.
Fine. So that is why what I am going to say, if I am going to consider, see the integral for the union, the line integral for the union this C1 pdx plus q dy. So then what it is going to give me? It is going to give me by Green's theorem. Del q del x minus del p del y dA. Is it okay? Fine. It is going to give me this. Is it okay? This is by the, whatever we have, derived previously. Okay, Green's theorem for a multiply connected region, right? Because this now becomes region with a hole. Okay, but now if you look at this, here, so here my P is this, Q is this. Here my P is this, and Q is this. And you can easily, if you evaluate del Q del Y, so okay. So what is going to be del Q del Y? Del Q del X. Del Q del X, it is going to be x squared plus y squared whole square. And see, in the numerator it is x, so 1 into x squared plus y squared minus your x into 2x, right? So basically, it is going to give me y squared minus x squared plus y squared whole square. Okay. Now, similarly, if you want to evaluate your del p del y, you can easily see that this is going to give you your x squared minus y squared. This is going to give you just this is going to give you this. Okay, so that means your del q del x minus del p del y, this is going to be equal to 0. Is it okay?
Yeah.
Fine. So from here, what I'm going to get? So this is going to give me Cp dx plus Q dy, and eventually this one, if I break it, so this is going to give me C1 P dx plus Q dy. So this is equal to 0. This is equal to 0. So that means from here I get the required integral, that is Q dy. So this is simply going to be equal to C1 P dx plus Q dy. Okay. So now what we are going to do, we are simply going to use polar coordinates. We are simply going to use polar coordinates for this curve C1. This curve C1. So you know that for that your x is going to be epsilon cos theta, y is going to be epsilon sin theta, and theta goes from 0 to 2 pi. Is it okay? Fine. So this is going to give you so theta going from 0 to 2 pi, and if you recall, I mean this becomes what? P. So P is this. So it is going to be minus y. Minus y is what? Epsilon sin theta by epsilon squared, and dx is going to be your minus epsilon sin theta d theta, and again here epsilon cos theta epsilon squared, and dy is going to be equal to epsilon cos theta d theta. Is it okay? Fine. So then from here you will see that this is simply epsilon squared within bracket sin square theta plus cos square theta, and that with this epsilon, that is going to cancel out. So eventually you are going to get 0 to 2 pi d theta, and this is nothing but 2 pi. Is it okay? Fine?
Yeah.
Okay. So this is about your Green's theorem. So now let us move to some concept called, Curl and Divergence. So basically what we are going to do, we are going to consider vector-value function. So say consider this f. Suppose your f is given by your pi plus qj plus rk, where your pqr, they have first order partial derivatives with respect, they possess first order partial derivative with respect to x, y, z in some domain D, say belonging to R3. Okay, fine. So then the curl of f, it is simply defined as this vector, your del r del y minus del q del j I plus del p del z minus del r del j plus del q del x minus del p del y k, del p del y k. Okay, So now what we are going to do, we are going to define the, in fact, see earlier also, we have defined the gradient of a scalar function. So what was this? This was simply del f xi plus del f del y j plus del f del z k, isn't it? So what I could have done, I could have simply, I mean, I could have simply written it as something like this, and like say, if I say that my this symbol nabla, it is simply equivalent to this operator So then what I'm going to do now. So basically, this operator now I'm going to introduce as the gradient operator. Okay, so let us call this as gradient operator. So if I use this, so then what we can do, we can define this curl of f. You will see curl of f to be something like this: cross product of the gradient operator and the vectorial function f. Why? Because if you see, for this, the components will be del x, del y, del zj, and for this components will be p, q, r. And you will see that once you expand it, you are simply going to get this one. Is it okay?
Yes.
Fine. In fact, I'm going to deal with certain examples in the tutorial sheet. But let me tell you that the concept of curl, I mean, it has a lot of application in fluid dynamics. Okay, and what they do, they associate curl with the rotation of a fluid. Why it is so? So suppose this vectorial function f that we have considered. So suppose it represents the velocity of a fluid in a certain domain. So if this is simply v, and so this is the velocity v, and suppose its components are say u, v, and w. So basically, u is the velocity components along x-axis, v along y, and w along z-axis. So then what happens? This curl, say, suppose I'm considering a point x, y, z in the fluid field. So then this curl of this v vector, so it is always this vector, it is always going to be along the axis about which the fluid is going to rotate. It is going to be something like this. So this is going to be curl of v. So this is where the concept of curl designating the rotation of a fluid comes from. Okay, so I'll be having one example, and from there you are going to get some insight. Okay, so now let us do some properties of curl, and you will see that this is pretty pretty straightforward. So for example, if say f is the gradient of a scalar function. So then this is simply going to be your one del f del x, del f del y, and del f del z, right? So basically your P, Q, R are given by this. Okay. So now then if you consider, I mean curl of F. So then what we get, firstly I get del R del Y minus del Q del Z. And we will have the other two components as well. J. Okay. Now let us look at it carefully. Okay. So if I assume that this function f possesses second order continuous partial derivative with respect to x, y, and z. So then what is going to happen? This del r is del f del z. So this is going to be del 2f del y del z, and q is del f del y. So this is going to give you del 2f del z del y. So if you apply Clairaut's theorem, so then I mean this is going to be 0. Is it okay? Fine. So
Yeah.
similarly, this is going to be 0. This is going to be 0. So that is why if f is the gradient of a scalar function, so then your curl of f gives you the 0 factor. Okay, fine. So can you make one comment from this?
Conservative.
Yes, because I know that whenever a vector field can be expressed as, I mean, gradient of a scalar function, we say that this is a conservative vector field, right? So that means for all conservative vector fields, the curl of them is 0. Okay, fine. Let me just quickly run through these slides a bit so that I have not missed anything. Okay, so this is Green's theorem on results with a whole. This we have already done it. Okay, and then this is the definition of curl. So this we have already proved. Okay, if f is a function of 3 variables, that is continuous second order partial derivative, then curl of grade f equal to 0, and this I have already explained. Okay, so this example 3 we are going to do it in our tutorial. Okay, so now again, as I have told you, I mean what is the conclusion from this theorem? That the curl of conservative vector fields is always 0. Okay. So now what I'm going to do, I'm going to come to the concept of divergence. Okay. So, and again, I haven't worked out any example on finding the curl of a vector function because that is very straightforward. You will have enough examples in your field, so that is why I'm not working out any example. Okay. So now let us come to divergence. Divergence of a vector. Okay. And again, we are assuming that we are giving a vector field given by this. Vector field given by this. Okay. So then the divergence of f it is denoted by this, and of course we assume that the components of f they possess first order continuous partial derivatives. So then this is defined simply as your del p del x plus del p del y plus del r. That's it is as easy as that. Okay, so again, this concept is very broadly used in fluid dynamics. Again, if f represents the and again, I have forgotten to tell you something. So when I told you that the if f is the velocity of a fluid in a certain domain, at each point, say, if f x y z denotes the velocity of fluid at each point of a fluid region. So then I told you that curl of F, it designates the rotation of the fluid. Okay, so that is why if the curl of F is 0, we say that the fluid is irrotational, and if it is not equal to 0, we say that the fluid is rotational. Okay, and likewise, if F represents the velocity of fluid at a point in a certain domain, and if so this is equal to 0, in fact, for any vector field, if this happens, we say that the field is solenoidal. But in case F represents the velocity of a fluid, then we say that the fluid is incompressible. Okay, and again, in your later years, if you are interested in fluid dynamics as your electives at some juncture, these are going to come in handy. So there is a very straightforward consequence of this your divergence. So this you can easily find out. No, I don't have to find it out. It's pretty straightforward from this definition. Okay. So what I will be interested in. So this one is also pretty straightforward. Divergence of the curl of any vector field is 0. Divergence of curl of any vector field is 0. Okay, so why it is so? Because if you look, so what is curl of F? This is what del R del y minus your del Q del what J, right? I plus E del Z Okay, so now if you have to find divergence of this, this function, so then what this is going to be? This is going to be del x of eventually what this is going to be? This is going to be your del x of this plus del y of this plus your del z of this. Okay. Now, if we assume that PQ are, possess second order continuous partial derivatives in the domain of definition of the function f, so then you will see that this term, where is r? It is going to be negated with this one, and so on. Is it okay?
Yeah.
Right? Okay. So this is about this divergence and curl in a nutshell. But you may be thinking why I am doing all this divergence and curl, because with the help of them, this Green's theorem, which we have done for a function of two variables, the Green's theorem, you'll be easily able to extend it to 3 dimensions. Okay. So, and again, let me tell you that whenever we consider curl, this curl is always a vector function, remember. And when we consider divergence, okay, we consider divergence of a vector field, it reduces to a scalar function. So you should remember that. Okay? So that is why when we say that divergence is 0, we simply use the scalar 0. But when we say that your curl is 0. So we are always going to use the vector notation. Remember that. Okay. So now what we are going to do, we are going to do this vector forms of Green's theorem. And you will see that this is so interesting. Vector forms of Green's theorem. Okay. And of course, so what we are going to do, the Green's theorem, I mean, on a plan. Oh, okay. So now, say, suppose I consider a function f, and I mean in 2D plan given by pi plus qj. So that means I mean if I will consider this function in 3 dimensions, the third component of this vector function it would have been 0, isn't it? So that is why if I want to find out the curl of f, so this is going to give me I j k, then del del x, del del y, del del z, p q. Third component is 0. Fine. So from here you can easily see that this turns out to be del q del x minus del q del y k, because the first components, 2 components will be 0. Is it okay? Fine. So now let us consider, I mean, Green's theorem on a plane. So that means if I have C as positively oriented, I mean piecewise smooth and simple closed curve that bounds a region D. So then I can t dx plus q dy, I can write it as this, isn't it? Fine. And from here, what I have got, this was simply d your del q del x dA, isn't it? And this I can write as isn't it? Fine?
Yeah.
So, and this is nothing but curl of f dot. Is it okay?
Yes.
Fine. Now, one thing. What is happening out here? Let me draw the figure. Say, suppose this is my curve C, and suppose this is the region bounded by C. Okay, and let us consider a point here. So now you can see that this one, if you recall, this one has been considered along the direction of R. I mean, if this point, say, if here this point is say xy, this point is say xy. So if I can describe this curve C through this parameterization. So then you know that, I mean, this vector is related to evaluating this line integral along the tangential direction of this curve. Is it okay? Fine? Isn't it? So now let us see what happens. I mean, if we consider, I mean, it along the normal direction. So this was the tangential direction. Suppose the normal direction is anything. I mean, unit normal. Okay. On that curve at this point P, say, if we consider this. So then what we are going to do, we are going to consider this integral. C ds. Okay. So basically what I am considering, say earlier, this was like p dx plus q dy. Okay. So it is line integral with respect to x and y. But now this is the line integral with respect to the arc length. I told you about the difference between these two, right? So how to find that out? And you will see that, I mean, that is also very, very interesting. That is also very, very interesting. So firstly, what we have to do, we have to find out the normal vector. We have to find out the normal vector, okay? Again, suppose your f is given by, your, I mean, p j, but we are assuming that any point xy, they can be considered as a function of the single variable t. So I mean this is simply p xt, comma yt I plus q xt, comma yt j. Is it okay? Fine. So now, in order to find out the, I mean, normal vector, to be precise, the unit normal, what we are going to do, we are firstly going to find out the tangent vector to the curve C at the point P. So then you know that this is simply what? This is simply given by r prime t by mod of r prime t. Is it okay? Fine?
Yes.
And this is simply your xti plus ytj, sorry, x prime t, y prime t, and this. I'll just keep it as this. Okay. Now you can easily check that a unit normal, it will be given by minus y prime t I plus x prime t j and this r prime t. So obviously, the first thing about this vector is that this should be a unit vector. Obviously, it is, right? Because I mean, mod of r prime t, and if you consider, right? And again, the dot product of these two should give you 0. You will see that they are going to give you 0. And this is I mean unit outward normal to the curve. Had you taken, I mean, y prime t minus x prime t, it would have given you the unit inward normal. Okay. So now let me consider this integral. Let me consider this integral. So if I consider this integral, so then you will see that, I mean, f dot n, from there your f dot n. So this is simply going to be your yeah. Yes. P xtyt, p minus p xtyt, y prime t, right? Y prime t plus q xtyt x prime t divided by r prime t. Is it okay?
Yes. Yes.
Fine. So let me just erase this. And if you recall, the value of this line integral, and if I consider this curve C to be such that it has been parameterized by RT, and if T lies between your A to B, then this is simply your A to B, and then your f as a function of t, and then ds becomes what your mod of r prime t dt. If you recall, this is what happens. Say, just a minute. Let me tell you. Say, suppose I'm considering something like small f of xy ds. So this was simply what? If you recall, a to b f of xt yt, then mod of r prime t dt. If you recall, because ds was what? Square root dx dt whole square plus dy dt whole square dt. If you recall, is it okay?
Yeah.
Fine. So that means if I use this above, so this is going to give me your a to b, say minus p your xt yt your y prime t dt plus your q xt yt your x prime prime dt. Okay, and if you recall, just okay, and if you recall, what is this? This is minus p. This is simply dy plus q dx, isn't it? If you recall, line integral with respect to x and y,
Yes.
right? And it is along the curve C. It is along the curve C. Okay. The very next interesting thing is that, so now again look at this. I can write it as your C q dx plus minus p dy. Right? Now if I use Green's theorem, this is going to become integration over this del del x of what? Just a minute.
Minus p.
Just a minute. Just a minute. Did I make some mistake here? Minus y del q minus p. Just a minute. Did I get the direction wrong? Just hold on for a minute. I just want to check whether. No, I made one mistake here. Just a minute. Why it is happening? Why it is happening? Like that n cap. Sorry, this n cap. Oh, n cap will be given by your this one. Your y prime t I minus x prime t z. I got the direction wrong. Okay, please correct it. Say n cap I have taken minus y prime t plus this, right? It should be this. It should be this. Okay? Right? So if it is so, so then this is going to be this one. This is going to be this one, and then this is going to become this. Am I okay? Yes. So then we dy minus yeah, it is fine now. So minus q dx plus p dy. Okay. So then it is going to become del del x of p minus del del y of minus q, right? And then it is going to be dA. Okay, so this is del p del x plus del q del y, your dA, right? And you know that this is nothing but what? Divergence of the function capital F,
Yeah.
right? So F dA. So F, this is what it becomes. Okay, so this is about your vector form of, Green's theorem. This is about vector form of Green's theorem. So in our next class, we would try to reach your surface integral, but before that, we will have to study about parametric surfaces and their areas. Okay, so till then, I will see you in my next class.